Alright, in this section here we're going to be talking about logarithmic functions. Logarithmic functions. And so in the previous section we talked about exponential functions. And to get started with logarithmic functions, we want to talk about finding the inverse now of y is equal to 2 to the x. So the function 2 to the x, alright, it does have an inverse. And if I were to write its inverse, we could say this. Remember, we just switched the x and the y. But remember, we need to get this as y is equal to, something or another here. And that something or another is what's known, abbreviated for the logarithm. The abbreviation of the logarithm, which I'm about to write. So this cannot be done using algebraic manipulation, and that is finding the inverse of this exponential function. Finding the inverse of this exponential function. So I'm going to write this. Y is equal to log, this is what's known as the base here, base 2 of x. Log base 2 of x, that's how this reads, log base 2 of x. And log is short for logarithm. Short for logarithm. Okay? So this is going to be the inverse of this guy up here. Right? Now we'd say, y to the negative 1, considering this is the inverse of this function here. Alright? Now the big part of this is going to be being able to go from this form here, alright, to this form. Okay, now remember, a must be greater than 0 if I haven't mentioned that, and a cannot equal 1. Okay, so this number here has got to be greater than 0 and it cannot equal 1. Alright. Okay, so let's just give some examples here. This may not be making any sense at this point, but I think maybe it eventually will. We have log base 8, okay, of 64 is equal to 2. Now this is in logarithmic form, and I want to rewrite this in exponential form. So you see this a right here, okay, or this 8, which is our a. We're going to write this as 8 raised to the second power is equal to 64. And we do know that 8 times 8 is 64. So just remember that this number down here gets moved diagonally, let's say to right here. Right? You see that? 8 squared is equal to 64. I should have probably wrote it like this. 64 is equal to 8 raised to the second power. So just remember, you take that and move it diagonally to here. Okay, and drop the log. Okay. Alright, we'll look at some more examples. What if I had log with a base 4 of 1 is equal to 0? So we take the 1, we just drop the log, rewrite the 1, move that 4 over. Right, I'm just trying to give you a way to remember this. So we know that a number raised to the 0 power is 1. Okay? A number raised to the 0 power is 1. So I could have a 5 here, or a 6, or a 7, or whatever. Right? As long as it's not, or it's greater than 0, not equal to 1. Okay? Let's look at another one here. What about if I had log base 27 of 9 is equal to x? So bringing this 27 over, raised to the x is equal to 9. You see that? So earlier we saw So in a previous section, we were talking about exponential equations like this one right here. We were wanting to figure out how to solve for x. Well, we can solve for x in this problem doing it algebraically. However, we're not going to have that luxury to be able to do that every time, and sometimes it'll be faster doing it a different way, and that is using logs. This logarithmic function, well, let's look at some more examples here of converting from exponential to logarithmic. So let's say that we had, I don't know, let's say we've got log 8, and this time we're going to have x squared plus x. So don't let this throw you off here. Now we want to go from logarithmic form to exponential form. So we're just going to rewrite this x squared plus x is equal to, and this becomes 8 to the first power. Okay, so now it is back in exponential form. Alright, let's look at something you might experience with a calculator. For example, let's say we had log of x plus 1 is equal to 4. Well, the question is, there's nothing written here. Okay, well, I guess that's not a question, that's a statement, but question is, what is supposed to be here, right? What is the base? And there's nothing here. Well, it turns out there's a 10. Okay, we just don't write it there. So there's assumed, if this is blank right here, there's assumed to be a 10 here. So that means we would write this as x plus 1 is equal to 10 to the fourth power. So on most calculators, you consider to be log base 10. And if you're trying to work something that has log base 3, well, then we'll have to know the properties of logarithms in order to do that. Okay, there's a way to rewrite this using the properties of logarithms, and I believe that's what I get into in the next section. Alright, so anyway, this is converting from log to exponential, and of course, if I had something like this and we wanted to go from exponential to logarithmic, right, we would say log base 3 of 10 is equal to x, So this is from exponential to logarithmic, and you will definitely need to know how to go back and forth between the two. Now, if I had a log base e of, let's say, 3, and that's equal to x. Alright, you're probably wondering, if you don't know, what is this number here? E is considered to be 2.71, and it's got some other stuff after that to infinity. So this number here is E, 2.71, you know, a lot like pi, which was yesterday, pi day, 3.1415926, and yada yada yada, on and on. But anyway, this is a transcendental number. It's an irrational number. And if we had base e here, we wouldn't write this like this. There's a shorter way of writing this, and we would say just ln. This is known as the natural log. We would say the natural log of 3 is equal to x. Okay, so that's the way we would write that. We wouldn't write that with the base e. If we're working with base e, then we write it just like this. Now, going from logarithmic to exponential, this would be 3 is equal to e, that's the base, raised to the x. So if we have e raised to the x is equal to 3, and we want to convert this from exponential form to logarithmic form, this is how we would do that. So I thought I needed to throw that in. So the main ones are e and 10, right? If this is blank, okay, then there's a 10 written here. If it's blank and it says ln, right, then that means that there's an e here, obviously, which is approximately this number here, 2.71. It goes on forever, yada yada yada. Alright. Alright, in previous section we talked about how to find the inverse of a function, and if we had y is equal to 2 to the x, we now know that the inverse of this function is log with a base 2 of x, and I should say write y, and this is really kind of y raised to the y. This is the inverse of y. And remember how we were able to tell if two functions were inverses each other by doing the composition of a function, taking this guy and plugging it in for x here and so forth, and taking this one, plugging it in for x, and we should both equal x. That was something that we talked about in a couple sections ago. But now basically what I want to do here is just graph these guys out and take a look at their graphs. So let's do that. Alright, this blue line right here is the graph of 2 raised to the x, okay, the exponential function, and then this graph here is the graph of log with a base 2 raised to the x. Now in most graphing utilities you can't just graph log with a base 2 of x. Alright, you've got to do something special to it, and we'll talk about that in the log properties. You'll have to rewrite that and to be able to actually graph it. But it's no big deal. And that also goes for plotting points, if we were to sketch this out by hand. But we can take a look at this because these are both inverse of each other, alright, and inverse functions of each other. And of course this is y is equal to x, and as you can see here they're a mirror image of each other. I'm going to, let's see, can we move the graph? Yeah, we can move it. As you can see here, as x gets closer and closer to 0, as you can see my y value decreases, right, is really decreasing here. Just kind of throw that in at you. Let's take a look at some others. Alright, this blue graph right here, this is a half raised to the x power, and then this graph here, you can see this has a base of a half, log base of a half of x, as you can see, decreasing. So let me actually write that out so you can see that. We have y is equal to a half raised to the x. Now that was the this part of the graph coming down and decreasing like this, and then so its inverse was going to be y is equal to log base is a half here of x. Alright, and remember that that's going to be a mirror image of this, and this actually, let's use a different color, it's green, we'll use green. And so this one's coming down like this, it's going to cross, it's going to be the intersection point right here, and then it's going to come down and do something like that. Alright, so remember both these graphs are a mirror image about the y is equal to x right here, as you can see. Okay, so this is just a little summary here on how to graph logarithmic functions and exponential functions, and noting that these are inverses of each other. And of course we talked about how to go from exponential form to logarithmic form. So this should give you at least a basic understanding of the log function, and I did talk about the natural log, and that's if the base here was e. Right, the base is e. In the next section we're going to be getting into the properties of logarithms, and then I think we're going to have some logarithmic equations where we're going to actually solve for x, because we're going to have things like, for example, this with this exponential equation here, where we're going to solve for x, and we're going to do that using the log function, or we could use the natural log function. It doesn't matter, you'll find out. But this is going to get down to being able to solve exponential equations where we weren't able to do this previously, especially something like this here. Alright?